In this video, we'll see the analysis of FET and MOSFET with fixed bias, self-bias and voltage divider bias using PSpice. The field effect transistor FET is a 3-terminal active device that uses an electric field to control the current flow, and it has a high input impedance which is useful in many circuits. The FET is based on the concept that charge on a nearby object can attract charges within a semiconductor channel. It consists of a semiconductor channel with the electrodes at either end, referred to as the drain and the source. A control electrode called the gate is placed in very close proximity to the channel so that its electric charge is able to affect the channel. In this way, the gate of the FET controls the flow of carriers, that is electrons or holes, flowing from the source to drain. It does this by controlling the size and shape of the conductive channel. The semiconductor channel where the current flow occurs may be either P-type or N-type. This gives rise to two types of FET known as P-channel and N-channel FETs. The DC bias of a FET device needs setting of gate source voltage VGS to give desired drain current ID. For a JFET, drain current is limited by the saturation current IDS. Since the FET has such a high input impedance that no gate current flows, and the DC voltage of the gate set by a fixed battery voltage is not affected or loaded by the FET. Resistor R2 is included to allow any AC signal applied through capacitor C to develop across R2. While any AC signal will develop across R2, the DC voltage drop across R2 is equal to I2R2, that is 0 volt. This is a circuit diagram of FET in fixed bias. Since no gate current flows through the reverse biased gate source, the gate current Ig is 0 and therefore Vg is also 0. Self-biasing of a JFET stabilizes its Q operating point against any change in its parameters like transconductance. The controlling gate to source voltage is determined by the voltage across Rs. The drain to source current is developed across Rs. The gate current is due to minority charge carriers, which is approximately equal to 0. Hence, voltage drop across Rg is 0, which is replaced by short circuit since Ig is 0 amps. Due to this, voltage across Rs gets appeared across gate and source. Hence, biasing is known as self-bias. This is a circuit diagram of self-bias for FET. The resistors R2 and R3 form a potential divider across drain supply. The voltage V3 across R3 provides the necessary bias. The additional gate resistor R2 from gate to supply voltage facilitates in larger adjustment of the DC bias point and permits use of larger valued R4. The gate is reverse biased so that Ig is 0. The circuit is so designed that IDR4 is greater than Vg so that VGS is negative. This provides correct bias voltage. This is a circuit diagram of FET with voltage divider bias. The IG FET or MOSFET, metal oxide semiconductor field effect transistor, is a voltage controlled field effect transistor that differs from a JFET in that it has a metal oxide gate electrode which is electrically insulated from the main semiconductor N channel or P channel by a very thin layer of insulating material, usually silicon dioxide. As the gate terminal is electrically isolated from the main current carrying channel between the drain and source, no current flows into the gate, and just like the JFET, the MOSFET also acts like a voltage controlled resistor where the current flowing through the main channel between the drain and source is proportional to the input voltage. Also like the JFET, the MOSFET's very high input resistance can easily accumulate large amounts of static charge, resulting in the MOSFET becoming easily damaged unless carefully handled or protected. The N-channel MOSFET has an N-channel region located in between the source and drain terminals. It is a 4-terminal device having the terminals as gate, drain, source and body. In this type of field effect transistor, the drain and source are heavily doped N+ region and the substrate or body are of P-type. The voltage at gate controls the operation of the MOSFET. In this case, both positive and negative voltages can be applied on the gate as it is insulated from the channel. With negative gate bias voltage, it acts as depletion MOSFET, while with positive gate bias voltage, it acts as an enhancement MOSFET. There are large variations in the characteristics of different types of MOSFETs, and hence the biasing must be done individually. This is a circuit diagram of MOSFET with fixed bias. The circuit diagram of MOSFET with self bias, and the circuit diagram of MOSFET with voltage divider bias. Now let's see the P-SPICE simulation for the various biasing of FET and MOSFET. Now let's design a circuit with FET using fixed bias. So to open a new workspace, we go to File and New. The new workspace opens up. Now let's start building the circuit. So first we'll place a JFET. We have placed the FET. Next we'll get the resistors. So since I have already used these parts in my circuit designing, it is available in this Dropbox. Suppose this is not available in the Dropbox, we can always go to get part, get new part. You can use this icon, or we can go to draw and place part. Or you can go and draw, get new part. So the library opens up, and from here we can select the required components. Next we'll place the resistors. So we can always change the alignment of the component by clicking Ctrl R. So for this circuit we require 3 resistors. So I am placing the resistors approximately for designing the circuit. Okay. So next we'll get the capacitors. After placing the capacitors, we'll get the voltages, the voltage supplies. Next we'll place the ground. Okay, now we have placed all the parts. Now let's connect them using the wire. So you can click on this icon, or we can go to draw menu and click on wire. So the wire gets selected. Now we can connect the parts using this wire. placing the voltage marker. Okay, now we have placed all the components and connected them. Now we give the values as per the circuit requirement. Now we can save the circuit. After saving the circuit, let's simulate it now. So we can either click on the simulate icon, or we can go to analysis menu and click on simulate. So the circuit gets simulated. So the simulation has completed. Now we can view the various input and voltage bias at the various nodes. Similarly, we can design the circuit of FET with self bias according to the circuit diagram, and we can give the values for the components as per the requirement. Then we can save the circuit and we can simulate it. Now the simulation has completed. Now we can check for the various bias points. So these are the voltage and current levels at different nodes of the self bias circuit. This is the voltage divider bias circuit of FET. So we have designed the circuit as per the circuit diagram, and the values for the various components are also changed according to the circuit diagram's requirement. Now after saving the circuit, we can simulate it. So the simulation has completed. Now we can view the bias points with the various voltage and current levels. So here, so R2 and R3 are the biasing resistors. So when we change the resistance values, the voltage will also vary accordingly. Now let's design the self-bias circuit of MOSFET. So we'll open a new workspace. We'll place a N-type MOSFET, which is N break N. We'll place it on the circuit. Now we'll select the resistors. Control R to change the alignment. Next VDC. And then ground. Now after placing all the parts, we'll connect them using the wire. Now we can change the values of the components as per the circuit requirement. Now we can save the circuit. After saving, we can simulate the circuit. Click on simulate icon. So the simulation has completed and the bias points have been calculated. You can see the various voltage and current levels in the circuit. Similarly, we can design the MOSFET with fixed bias. After giving the required values for the components, we can save the circuit and simulate it. So the simulation has completed and the bias points have been calculated. You can view the voltage and current levels. This is a circuit diagram of MOSFET with voltage divider bias. So after building the circuit as per the circuit diagram, we will have to give the required values for the various components and save the circuit. Then we can simulate the circuit. So the simulation has completed and the bias points are calculated. These are the voltage and current levels at various nodes of the circuit. Thus the FET and MOSFET have been designed and simulated for the various biasing circuits.